Good afternoon, folks. We've got a good crew coming in here as we kind of wait for everybody to log in and join the webinar here this afternoon. So we're just going to give everybody maybe a half minute or so just to get logged in. First, we appreciate you guys being part of the LSAAT community, being willing to engage late in the afternoon if you're on the East Coast, or maybe while you're taking your lunch on the West Coast, or wherever you are in the world. We appreciate you being part of this community. If you don't know LSAAT, Large Scale Additive Action Team, right? This organization has really stood up to help facilitate the large scale additive community in helping to go from the research stage to the transition and implementation stage, really across a wide range of technologies, a wide range of sectors. But we're really here to try and make sure that there's a platform for communication to talk about the hard problems, to talk about the upcoming opportunities, to share information, the wins, the successes, and sometimes the challenges, right? And so every year we host the Cold Spray Action Team and the Large Scale Additive Action Team in Worcester, Massachusetts. That's in June each year. You can go to the respective websites to see more information about that. But as part of kind of our effort to ensure that we have a really good dialogue with the community, what we wanted to do is actually start bringing in some of the leading experts in this space, in the transition of technology, to talk about the challenges, the opportunities, and the approaches that are being taken. And for those of you that are in the large-scale additive space, you know that one of the leaders in this sector is the U.S. Navy, and in particular NAVSEA and their efforts to really stand up a robust process for going from problem identification in terms of parts, availability, supply, to kind of technology identification, the different available platforms, whether it's the companies or it's the individual technologies, the materials, and then the actual end implementation process, what that qualification looks like, what the requalification looks like. And really one of the leaders in that space, and who was described to me as being a mover, a shaker, and a doer in all things additive, is Dr. Kevin Jensen, who's the AM engineering manager with NAVSEA, and has really been driving a lot of this effort along with some other key folks in that organization, to help make sure that there's a viable pathway forward. And so we really are excited to have Kevin spend a few minutes sharing with us the opportunities that he sees, the challenges that he sees, some of the stories that he's seen as well. And we invite you guys to use the Q&A button down at the bottom, submit any questions that you have along the way here. And when we get to the end, we'll do kind of an open forum. So I'll facilitate the conversation. We'll try to make sure that we've got plenty of time for that question and answer. But if there's anything specific that you want to dive into, please feel free to do so. Do remember that this is a recorded webinar. This will go live. This is not a controlled environment. So this is all public conversation. So please keep that in mind. But otherwise, without further ado, Dr. Jensen, I want to kick it over to you and have you just kind of blow us away with everything that you guys are up to.
Oh, well, with that level of buildup, I have to do pretty well, I suppose.
We know you will.
Thank you very much. So, thank you, everybody. I really do appreciate this opportunity to share where the Navy is with additive manufacturing, with the large scale additive community in particular, because so much of our application space is on larger parts and components which are going to exceed the bounds of what is typically seen in AM. So my name is Kevin Jensen. I am an engineering manager for additive manufacturing in the Naval Sea Systems Command Technology Office. It's NAVSEA 05T. I work directly underneath the warrant holder for additive manufacturing, Dr. Justin Mortagliata. The Navy Tech Authority system uses a series of warrant holders who are responsible for championing and spearheading various technologies and systems. There's a warrant holder for piping. There's a warrant holder for non-ferrous materials. And Dr. Mortagliata is the warrant holder for additive manufacturing, which means that it is his job to handle policy and to ensure that the level of technical rigor is appropriate for Navy needs. So the first thing we're going to show is this kind of very high level approach of how of how the Navy handles their how the Navy is envisioning additive manufacturing. And it's a two-pronged approach. On the upper level, where the higher risk components are, we are partnering with academia, we're consolidating our data, we're getting this material maturity approach, and we're basically saying, what do we have to do to ensure technical rigor and have confidence in making the components which, if they fail, will result in the loss of life, loss of a submarine or an aircraft carrier, where failure is not an option. And how do we ensure that level of technical rigor? And we are looking at using additive manufacturing for those components. On the other side of it is, what can we do to push AM and establish confidence in the technology? And the approach there is, we focus on parts where if they fail, it is not necessarily good, but it is not crippling. And so, for example, if a deck drain fails, if it cracks, well, it's not great, but it is not going to sink the ship. And so we are using those low risk parts to activate industrial partners, to establish confidence in the process. And the long-term goal for all of this is get to the perspective where we have manufacturing specifications that ultimately allow us to unlock additive manufacturing as an interchangeable manufacturing process. And what that means is that we want to be in a situation where we consider additive manufacturing, and obviously additive manufacturing is not just a single technology, but the breadth of technologies that can be offered with additive manufacturing are as interchangeable as going from a casting to a forging to a machined billet, where we know we have confidence in the process, we have confidence in the output, and we can then turn around and make sure that what we deliver is of a level of quality necessary. And at the same time that we're doing that, we are also looking at deploying additive manufacturing, putting printers, both plastic and metal, on vessels so that we can then establish the immediate benefits of AM in that area. For example, manufacturing critical components or components which are missing or damaged and allowing us to maintain that sustainment. So how does one handle additive manufacturing? Well, there are a lot of considerations that we have to look at. On the left-hand side are just the necessary components applicable to the actual component or part. You have to think about how big the part is, how is it shaped, what kind of material properties are necessary, and what is the criticality of those material properties. If the tensile strength has to be a certain value, and if that tensile strength fails, and you lose a boat, we have to understand that and establish a level of rigor appropriate to that criticality. Beyond the raw material properties, you have application and performance requirements. Just because you 3D print something doesn't mean you can skip functional testing, doesn't mean that you can disregard your environmental requirements or pressure retaining or anything like that. And then finally, we have to understand what our vendor base can do and what machines are available. And once we have all of those combinations, we allow that to create a selection of what we call an MPC, material process combination. For example, 316L laser powder bed fusion was a material process combination. Copper nickel directed energy deposition using wire arc is an MPC. They're going to be different. The requirements and the output and the artistry is going to be different from each one. Once you have an MPC selected, you then need to incorporate your business and legal considerations. Can we reverse engineer the part? We have a policy in place, it is government approved, that allows us to reverse engineer components when it's done by the government and there is an imminent need that cannot be met by industry. As the government, we have the right to make sure that our vessels are capable of defending our country. And then at the same time, we have what's known as the psychological readiness level. This is a term that Dr. Italiata came up with and loves to talk about. And that's basically understanding that additive manufacturing is not as well understood as, say, a casting or a machine part. And you have to make sure that everyone who is involved in the approval chain, whether it is an engineer who's designing the part or the program office which is funding it, is confident in the application. And that's where the psychological readiness level comes into. All of those things flow together to ideally making a part. Now, outside the bounds of those NPCs, there are a lot of processes that we're interested in. And what we have here is a pretty picture that shows all of the 7 core AM fields for the I think it's the ISO definition, as well as some of those sub areas. And areas that have a blue dot next to them are areas that Navy NAVSEA is either has an existing process standard or is working on establishing a standard. And the major ones are laser and electron beam powder bed fusion. We are looking at developing a process qualification for metal binder jetting. We have investments in polymer material extrusion. We're very close to having a technical publication for polymer and composite material extrusion. We have an existing tech. We're also looking at friction stir and material extrusion. We have a technology publication for wire arc directed energy deposition, and we're also expanding that to powder laser. And then we're not doing much with vat photopolymerization or sheet lamination because as useful as those processes are, most of our focus is on metals. Speaking of what materials we care about, this chart is particularly important. And on the left side are the 6 materials of that the Navy submarine industrial base, which is now called the maritime industrial base, are focusing on for AM. First one is MIL 100S. This is a welding wire that is a legacy replacement for cast HY80, which is a high strength structural steel used in submarine hulls and other major components. We have nickel aluminum bronze, which is extensively used in impellers and propellers and fluid handling systems. We have copper nickel. That's a 70-30 blend of copper and nickel. That is extremely prolific through many of our systems. A lot of our piping structures use it. Anywhere that we're concerned about corrosion, it exists. There's also a 316L stainless steel. This is actually not just 316L, but kind of covers the entire family of what's called CREST, corrosion resistant eutenic steels, I think it is. That is going to be steels which we know will be in a corrosive environment, but may not necessarily be subjected to the level of environmental hazards that, say, a copper nickel or nickel aluminum bronze will face. Inconel 625, alloy 625 is used extensively in high temperature systems, gas turbines. And then titanium is of interest. It's used a lot in our more corrosive piping systems, for example, a lot of our fire suppression equipment. And in the middle, you can see the processes of interest. Many of them are focused on wire arc DED. Actually, all of them have a wire arc DED component. And that is because we expect that the priority for us is that large scale additive component. We need to be able to make big things because we are replacing castings and other larger structures. DED is extensively used, and then we also have LPBF for copper nickel, 316L, and alloy 625. And on the right are what we have are what's called the PPDs, Project Peculiar Documents. These are the initial stepping stones for the material specification that is necessary for us to establish contractually what this material has to do. And I need to emphasize that this is preliminary. We have a document out there, for example, for copper nickel laser powder bed fusion. That document specifies what the chemistry has to be. It specifies what the material properties have to be in terms of yield strength, ultimate strength, and elongation. It is the stepping stone that we are using to establish what's called a material maturation team, MMT. And those efforts are there to establish exactly what that particular MPC is going to do to a statistically rigorous level of understanding. The long-term goal being that every single one of these MPCs is going to have a military spec material specification. I think it's going to be a MIL DTL, but don't the exotic requirements of the MIL standard realm are something I'm still exploring. But it will be a standard, it will be a MIL spec, and it will be something that the Navy spearheads to be used across the entire industrial base. To support those particular MPCs, the Navy has been extremely prolific in making technical documentations. Back in 2018, we created the NAVSEAT guidance on the use of additive manufacturing. This was our line in the sand for how AM is approved. What does that decision tree look like? Who has to approve it? And what materials can be used aboard ship? Obviously, 2018 is forever ago when it comes to a technology as advancing as rapidly as additive manufacturing. And we are in the process of revising this guidance to take advantage of a lot of the efforts and understanding that have matured since then. An example of that maturation is the guidance on identification installation of low risk manufactured components. This is what we call the low risk letter. This was issued as publicly releasable back in May of this year. What this document does is it says this material, this particular application is of so low risk that you are allowed to use laser powder bed or directed energy deposition without approval from NAVSEAT. Components like deck drain covers, louvers, a lot of hand wheels, components which we want to get printed, we want to get fielded, and we know it's okay if they fail. We don't want them to fail, and we are trusting our design agents to execute due diligence, but we don't necessarily need to watch over those components to the level of specificity that, say, a sub-safe part would require. We have two tech pubs, one for directed energy deposition and one for laser powder bed fusion, specifically wire DED. These were both issued with they were both revised of this year. And what they do is they provide the guidance for establishing how a particular machine and vendor has to be qualified. Qualification is the stepping stone for allowing vendors to print high quality components. It allows us to show to a level of confidence that the Navy has established that a machine is consistent. It shows that the vendor knows what they're doing, that they have the right process controls in place, that they have the right training regimen in place, that they have the right material control, that everything is done up to a level of quality which will ensure a critical component is manufactured. There is also a lot of work done on NDT, non-destructive testing. Unfortunately, additively manufactured components have an internal microstructure, which is a nightmare and makes it very difficult to use legacy NDT methods like ultrasonic testing or related efforts. There is some work on X-ray CT, but you can't necessarily XRCT everything, especially when you're talking about parts that are as bulky as a lot of Navy applications. We also have the material specs, those PPDs, both for, this was released in two groups. The first one being a series of PPDs specific to 316L, copper titanium, commercially pure titanium, 7030 copper nickel, and then nickel aluminum bronze. And then we also did a second one specific to MIL 100S, because MIL 100S within the context of the Navy is its own beast. It requires very specific levels of control and maturity, and so it's a separate effort compared to the others. In terms of where things are being produced, a lot of what we're doing right now is addressing point of need situations where the supply system has failed us. And that means situations where it's going to take us months to get a component and the boat has to leave in weeks. Components that the shipbuilder is excited to see. CANAB or cannibalization lists, meaning that when one vessel comes in, the first thing they do is they immediately start stripping off parts that can then go to other vessels. They cannibalize the vessel that just came in so that other vessels can get out. Well, that creates a pretty nasty cycle. And so part of our goal is to utilize that list to establish what our high priority components are. And what we have here is a series of examples of installs. A lot of these are low risk. The ventilation louver went on a submarine. The bilge strainer is a component that normally gets corroded very quickly. The sprayer plate there was manufactured using a shipboard AM, and I'll cover that in a bit. And then the sanitary pressure valve was one of the first copper nickel components that was manufactured using LPBF. That is actually an example of something that wasn't low risk. It was just on the threshold, and we evaluated and accepted that. These are some examples, just additional examples. We have drain strainers, release mechanisms, door hinges. The main thing here is that these are all components which individually don't necessarily seem like much, but what they represent is the fact that we are seeing metal components get out in the field, and that it's enabling us to say additive manufacturing is not as scary as you would think. And in FY24, we have, for example, this proximity switch bracket, which was a pain in the butt to manufacture, and we were able to 3D print them very quickly. And on the right, you can see some of the really bigger parts. I mean, that manifold there is, I think, 4 feet long. That's going to be used for, that's made out of 316L, and it's actually, I think it's a JP8 manifold, so it's going to have jet fuel running through it. And then on the other side, you can see this strainer component, which is also a fairly sizable aspect. We are working closely with industry. An example of this is our work with Fairbanks Morse Defense. This is all done through the Maritime Sustainment Technology and Innovation Consortium, the MISTIC, OTA, Other Transactional Authority. And in this case, it was a 70-pound copper nickel valve assembly that's replacing a traditional sand casting. They used a wire art DED, which you can see on the left-hand side, and it's producing significant benefits. Reduction in lead times, reduction in waste material, and allow us to make a component with a much, the turnaround time is probably our biggest benefit here. We are deploying additive manufacturing. This is something done directly underneath NAV CO5T. CO5 is supporting both metal and polymer. You can see here this is a hybrid metal AM system. It is a Haas TM1 machining center with a Meltio laser wire DED system attached. It runs in 316L. And you can see examples of components that were manufactured down on the right. There was a custom stromback that you tie to piping to help support it, and that prevented a leak. And then a sprayer plate down there, which was actually produced on the Wasp, or was it the Baton? I think it was the Wasp. And this is this is the Baton. This is an example of that process that was used to use fielded AM, an AM process on ship to manufacture this point of need. So what happened was the Baton had a deballasting compressor housing, and they found that a sprayer plate was somehow missing. It's not a terribly complex component. It's maybe 6 inches wide, but it allows oil to be sprayed inside the mechanism, inside the compressor, and it maintains reliability. Normally, you would spend, I think it was $250,000 to replace the entire system. But what the sailors on the Baton did was they grabbed a sprayer plate off of a different compressor. They used a combination of calipers and CAD to make an initial model. That model was then sent to the NAVSEA Apollo lab located in Carter Rock, where they refined the model and they did a test run locally using their own Meltio system, and made sure that it could be manufactured using only the tooling that was available on ship. So for example, they had a drill bit that wasn't long enough to go through the entire length of the component, so they had to make sure they could drill it on both sides and that it could be manufactured using only what was on ship. They fabricated it, they machined it, they cut it off the plate, they did finish machining, and they installed it. You can see there that from model to installation was less than a week. And that is the kind of benefit that we're seeing additive manufacturing provide when fielded. Another example, there was a shipboard optical landing system. It's a very large critical component. And what they need to do is they had a shaft coupler. It was between the motor and the pump system. And this is a small piece of plastic which is designed to fail so that you don't break something expensive. Well, it failed and they didn't have a replacement. So the Apollo lab was able to model and demonstrate how to print a replacement. And in 2 days later, it was installed and it worked fine. Another example is a gearing housing, which was necessary on a ship on a surface search radar. And what they found was that there were missing teeth on this component. They were able to reverse engineer and print the replacement in 3 hours, which is a good example of how a component which would not have been able to function to the level required was able to be manufactured and installed in a timeline that is previously unheard of. So that is the overall brief I have. I'm sure there are plenty of questions. This is the contact info for myself as well as Dr. Italiata. I'm happy to answer any questions or address any inquiries. And since I know this is probably going to be the most pertinent information, the last slide I have is the list of all of the technical publications on the left. We're happy to release those to anyone who needs them. They're all distribution A, meaning that the distribution is as unlimited as this document. And on the right is the material process combinations that are critical to the existing Navy interest. So with that, feel free to answer any questions.
Awesome. Thank you, Kevin. That was fabulous. And you're very wise for putting this slide at the end, because you're right. You're gonna have to go back to that slide like 10 different times. So this is perfect. And you really hit on, a whole bunch of really important topics along the way. And I think one of the kind of initial underlying questions that kind of keeps popping up is, where do you guys see the pipeline of different technologies coming into bear with kind of the Navy's development path, right? So today it's the kind of wire arc DED and the LPBF, and you're kind of slowly opening up the aperture to other technologies, like you talked about the laser powder DED and the laser wire DED. How do you guys decide kind of what you're going to focus on next, and what other technologies are on the horizon?
So it's a combination of factors. The first one is where are these technology? What are the needs? Meaning, am I not able to manufacture a component using laser powder bed fusion? Okay, well, DED can do it. Is DED the right choice? Do I need it faster than that? Well, binder jetting offers a completely different method of producing it. So that's the next material, that's the next process on deck. And that is something that we're going to put a tech pub together. To introduce newer technologies that don't necessarily have that level of maturity or installation, we are revising the guidance letter, the 2018 letter, so that it is more flexible in allowing these commercially available processes to be used on things like what is currently called low risk, but in the future will likely be called subcritical and non-critical applications. And the idea being that if it's non-critical, there will be no restrictions on what process is being used as long as it's commercially available. And if the component is subcritical, then it needs to be manufactured using using a process which is qualified to some extent, whether it's a NAVSE tech pub or AWSD 20, for example.
Got it. And I think that tees up nicely sort of the follow-up question, which I told you we were going to get, which is within the kind of AM community, very frequently cold spray additive manufacturing is one of those technologies that is not quite considered additive manufacturing, although I know numerous individuals are trying to convince the powers that be that that's wrong. So I'm curious your take on where cold spray fits in the Navy's portfolio from an additive perspective, but then also just from an overarching perspective.
So I will fully admit cold spray is a technology that I have some familiarity with for R&D. I am not an expert on cold spray. I love solid state. I love the way we can beat the daylights out of metal powder and have it do what we want. I'm all for that. In terms of implementation, we are seeing cold spray already being used for repair. There are processes and policy in place for cold spray repair. In terms of cold spray additive, we are aware of it. We are seeing some push to see it be implemented due to the speed it offers and some of the unique material properties. Where it falls within the NAVC portfolio is that we currently do not have a plan to put a tech pub in. However, we are exploring whether or not we need to change that. We are using the technology office to start making initial investments in cold spray additive and establish what need would cold spray provide that is not currently addressed by LPBF, DED, and binder jet. And that's the biggest thing. What does the Navy need, and how does that Navy need translate to something unique to a new MPC?
Awesome. Yeah, I think that's helpful. And I know from the broader LSAT community, right, coming out of the cold spray action team, there's a lot of folks who are deeply entrenched in the cold spray additive side of things. So I'm sure if we put out an open call, you'd have about 10 different white papers from the team here trying to convince you that cold spray additive is real and ready for prime time. So
I mean, I've seen cold spray additive. It's cool. I like it. I like what Speed 3D is doing. I know that they're not the only game in town.
yep,
There are avenues that I want to see invested. So
yep.
don't think that I don't know what cold spray does, and trust me, there are aspects of it that I really like.
Absolutely. So kind of moving away from the process side for a second, and thinking about some of the materials and material direction, and this may tie back into processes in a minute anyhow. Um, where do you see the pipeline of materials outside of kind of the current, what do we have, 5 or 6 here, out into the future? Obviously, these are the kind of majority, the critical ones. That's why you're focused on them. But in terms of kind of other alloy considerations that are of interest, what do you
Sure.
guys see kind of on the horizon, especially around different aluminum alloys and other kind of lightweighting alloys?
So aluminum is one of those materials that NAVC, meaning Naval Sea Systems Command, is less interested in, but NAVAIR is very much excited for. And we work closely with our colleagues on the NAVAIR side. They are doing a lot of and so along with our colleagues in the Air Force, and I know the Marine Corps likes using aluminum for lightweighting. It is I will fully admit I do not have the level of experience with aluminum that I have with, say, 369L, copper, nickel, or those materials. I can say that it is not as much of a priority for the surface fleet or the subsurface fleet, but we are leveraging the work that our partners in NAVAIR are doing, as well as the Air Force in that regard. Other materials of interest, there's a lot of interest in high strength steels, 4340, miraging steels, things which are necessary for a variety of applications, whether it's structural applications. I would be remiss if I didn't say we have interest in high density alloys, tungsten, nickel, iron, anything that can be used for, well, for certain packages that are not the kind of thing I could talk about in a destroying environment. Those are the big ones, but I would say that a lot of what drives our interest is volume and the need to support the submarine industrial base effort. The demand signal for one Columbia class submarine, the raw material required to manufacture one Columbia class, is more than the entire additive manufacturing industry in CONUS can actually make right now. It's something like 100,000 tons, and it's a lot.
That sounds about right. And I
Yeah.
think that tees up kind of one of the next questions here, which is when you think about the growth of additive manufacturing, right? There's the entire kind of SIB, or I guess now MIB, right? Is really looking at this. And you touched on NDT a little bit, and we're talking about system availability. But what do you see as really some of the underlying fundamental blockers to moving even faster to keep up with demand for things like the AUKUS production capacity and others? What are some of those key blockers that you see that this community should start thinking about how to address?
So I would say the biggest blockers, the first one is confidence in the material properties, understanding what a particular MPC actually produces. What is the yield strength, ultimate strength, elongation, impact toughness, fracture toughness, corrosion response is huge. And then understanding how those properties respond to changes in geometry, changes in build quality, all of the little nuances required to have confidence in this in just a single machine making a single part. Expanding beyond that, we need to have a statistically rigorous understanding of what it is that we can do to show that a particular vendor, when they make their stuff, it is in that we understand what the definition of quality is, what level of variation should we expect sample to sample, and when do we see something that is out of family. When is a vendor being a bad actor? When do they say they heat treated something and they didn't do it right? When did they start using bad powder or bad feedstock? Can we capture what that looks like? And then beyond that, probably the other really big challenge is going to be NDT. And a lot of what we do right now is relying on XRCT and other things that may not necessarily be scalable. And I think the solution there long term is going to be in situ assessment. We are seeing that a lot. The SIB is investing a lot in the use of ISA, with the long-term goal to hit that what is called born qualified. The idea being that the part is good to go once it's out of the machine. And the reason we know it's good to go is because we had something monitoring it and it knows how it's supposed to work. Excuse me. So very base level, confidence in our material, level above that, confidence in our process, level above that, leveraging the unique capabilities of AM to start escaping beyond the legacy approach.
Awesome. I think there's a bunch there to unpack, maybe kind of like one at a time, if you're okay with it. So this ties into one of the other questions that we have, which is, thinking about confidence in materials. What can you provide to the team here as far as kind of the confidence in ability of vendors to hit material properties today around the kind of MPCs of interest? So thinking about like especially the titanium, the nickel and bronze, the copper nickels. Where is that from your perspective?
I'd say it's pretty high. Like, we have vendors out there who know what they're doing and who have made a particular process their bread and butter, and they understand it in and out. One of the first vendors that we qualified was Kozlowski Additive Manufacturing out of North Carolina, and they utilize laser powder bed fusion in a very robust manner, and the output they have is of high quality. Johns Hopkins APL did a study I think it was last year, where they compared the output of different vendors. And what they found is that when everyone's doing their job, the tolerance bands are extremely tight, tighter than you would think. And because that is tight when they're doing things the right way, it means that they can catch the people who aren't doing their job. And they found that, oh, these people are all over the place. Why is that? Oh, they didn't heat treat it the same way everyone else did. Oh, they didn't machine it. They didn't machine these samples the right way. Capturing that shows that it's possible and really gives a lot of confidence in AM.
Awesome. And I think the follow-up question there is kind of in and around a lot of the maybe supporting data. Like, what is it that helps to build that confidence for the Navy team that other processes or other material systems should be looking for? Are there, in kind of the aerospace community, we've got the different allowables. And I'm curious if there's kind of a similar standard that's being developed within the NAVSEA TechPub system.
Oh, there very much is a standard. It's one of my hats. Is to one of the questions that we're trying to answer in the guidance letter is, if I have a critical material property, how much testing do we have to show to achieve statistical confidence in that to an A basis? 99% probability, 95% confidence. How many tests do we need to run? What kind of overage relative to that threshold needs to be demonstrated based on those tests? It's very similar to what you're seeing with MMPDS with their S basis and statistical analysis. I mean, statistics hasn't really changed. which is helpful for us. We just have to make sure that the process that we're executing is the right balance of robust, but accommodating the needs of the industrial base who do not necessarily want to have to make 300 tensile bars just to show that their system was fine. So it's going there are basically two paths. The first path is what I talked about there for a material process combination that doesn't necessarily have the level of rigor or understanding or utilization that establishes a material standard. And on the other side of it is the material standard. Our goal is to have specs for these 6 critical material process combinations. And what that means for us is that we're going to have what's called the material. The material will be matured to the point where we understand what it is it's supposed to do. What is that tolerance gap? What is it you can contractually demand of a vendor? For example, DED, nickel, aluminum.
Got it. I think that's really helpful. I'll give you the really fun, very, very explicit question from one of our attendees, which dovetails off of this is, have any of the companies hit 100% of the properties for NAB C964 and the copper nickel B369?
Yes, I believe so. I don't recall exactly what the numbers are, and I know that they're still working on everything, but my recollection is that they are showing a high level of confidence that they can meet those legacy processes, the legacy material properties. And part of the reason that we have that confidence is that, we've done a lot of that work with the understanding that if we couldn't reach that material property, we weren't going to continue to invest. So every single one of these MPCs is something where we have confidence it's going to do what we need it to do.
Right. I think that is spot on. And I think that from at least the outside perspective, kind of looking in, very consistent with the way that NAVSEA has made kind of investment in this space. And it's been it's been very nice to see from the kind of industry perspective that there's kind of a rhyme and a reason to the process here, based on kind of real need sectors. So I think that's huge.
And the other thing we're willing to accept is that we're not perfect. We make mistakes, and that sometimes we demand more than is reasonable of our industrial partners. And a perfect example of that is our tech pubs. Rev 0 for our tech pubs required way more testing than Rev 1 does. And that was because we were able to look at the data, look at the science, and go, no, you don't need to make that many tests. You can do this many tests, and it's significantly fewer.
Yes, we had fun with that.
Oh, yeah.
So a kind of follow-on question then, getting into the NDT layer of the challenges is, obviously maybe first a definition, right? When we talk large additive, everybody has kind of a different perspective. What does that mean to the Navy?
I think large, it depends on the process is one way to be really cheap about it. I'll say I consider large to be something I can't pick up, and I'm 6'9" and 300 pounds. So that's a good starting point. I would say it's less about what we define as large and more about acknowledging that we have parts that range from hundreds of pounds to thousands of pounds. That 70-pound copper nickel valve we talked about with the defense company, that is a big part in the context of, say, laser powder bed. That is a part that will take weeks to manufacture. DED, not necessarily. But DED, we're making parts that weigh 10,000 pounds. We have parts that are exceeding the capacity of our robotic arms. So it's less about, like everything else, it depends. And
Yep.
that actually reflects a fun frustration with additive manufacturing, and that it's not just one process. A large casting is different from a large machining, is different from a large forging. A large LPBF part is different from a large DED part.
Yeah, I think that's spot on. And we're gonna kindly ask if we can use that definition of large additive for LSAT.
You're welcome to. Anything that Kevin can't
Excellent.
pick up. Now Excellent. I have to thank you. Now I have to hit the gym. I've played myself.
Perfect. Diving into that NDT piece a bit, and knowing that large does mean everything from a few pounds to tens of thousands of pounds, and knowing the challenges with the microstructure that we're seeing, are there any approaches on the horizon from the post-process NDT perspective that you see maintaining viability long term, or is everything really towards that sort of born qualified approach? And if so, how do you expect to kind of see that realized? What is the process going to be in terms of investment, sensing, and kind of the related technologies to get to that level of confidence to have that sort of certification?
The good news is that the Navy will release a guidance letter on how we want to see ISA implemented in the next few months. It is a multi-step process. It starts with understanding the spectrum of available sensing capabilities that are out there, and then understanding how those sensing capabilities are going to be put together for each possible MPC. And then understanding from the Navy perspective, really what it is we can and can't do with ISA. Because like most technologies, there's what you think it's going to do. There's what the people being paid to do it are going to tell you what it's going to do. And then there's what it's actually going to do. And it's very difficult to establish policy without having a robust understanding of exactly where it will be and what it can and can't do. So the NAVSEA ISA approach right now is to make intelligent investments, and as we see the ISA process mature, as we see vendors start to incorporate it into their technology, we then leverage that to be flexible and establish guidance letters, and then ultimately a manual.
Got it. I think that picks up a thread then of knowing that this is coming down the pipeline, and also all the other developments that are going on within the Navy. Just kind of broadly understanding for this community, what are the best ways to get involved in solving some of those problems, right? This webinar is great for teeing up a lot of those challenges, but for the folks on the call that are not directly engaged with you guys today, what are the right approaches? What are the right platforms? Are they paying attention on Facebook and Twitter or X or whatever we are now, or are there better platforms to be paying attention to how to help solve Navy problems?
So the best platforms are to engage with the submarine industrial base program through the Mystic OTA. That is one of the primary funding vehicles we are using to advance large scale additive in particular, and then also we have academic partnerships there. The other avenue is the Center of Excellence located in Danville, Virginia. They are serving as one of our primary partners for establishing vendors for qualification certification. And I guess it depends on what you want to do. If you want to make parts, then getting into that vendor pipeline and showing that, oh, we have the chops to make this and we can get our processes qualified is that right step. And then, or if you want to help with Mystic OTA, there's a lot of opportunities there.
What about from more of the sort of lower TRL research side, especially thinking about some of the in-process monitoring? What are some of the avenues that you engage in, some of those kind of like lower TRL, more research oriented, especially for some of the university partners that are online?
So there are university partners for the Mystic OTA. We use them. And then you can also, if you contact me directly, I can link you up with, we have a very robust AM program through the Office of Naval Research, ONR. They have a ton of academic partners, and we're always excited to see where that low TRL, high potential technology can be guided. And Dr. Jen Woke, who runs that, is a phenomenal individual and is definitely someone to know.
Excellent. And you talked about one thing there in terms of engaging with SIB and SIB related activities. And I know there's the new kind of maritime industrial base has come out as well. And just curious if you could shed some light on that for the community as far as any changes that are resulting from that, or if it's really just kind of a rebranding.
It's a combination of rebranding and an increase in scope. Basically, I will fully admit I am not completely briefed on how everything changes. From my perspective, I still have to focus on additive manufacturing, but it's basically, as I understand it, a reflection of the fact that this is a really, really important thing. The industrial base for our defense community is not something that can fail. We have to be able to manufacture these critical assets as part of our nuclear triad, as part of our deterrence, as part of our collaboration with our partners through AUKUS. And so this is something that we just have to make that investment in. And the thing that we've come to accept is that this is not just a submarine problem. This is a maritime problem. And so because a lot of the lessons learned on a boat can apply to a ship, we're hoping to make this as expansive and useful as possible.
Yeah, and I think that, really highlights the criticality just across, the whole industry. And I'm curious, one of the challenges that kind of has been identified and kind of pops into some of the questions here is, Navy's done a great job of sort of leading the charge. It even applies, in some cases, more forward thinking than even folks in industry have been. And so, how do you see other folks in the other services, in industry, or outside of the U.S. Starting to either adopt Navy practices, Navy documents? How do you support and facilitate that, or do you see us going into a world where the AM community has to deal with 15 different specs and standards just for one process and one material without kind of the uniformity behind it?
I guarantee you that we do not want the industrial community to have to deal with 15 different specs and standards. That down that path lies madness, and nobody wants that. A lot of it that I have seen is the entities, not just DoD, but also DHS, through especially Coast Guard. Coast Guard and Navy work very closely together because our application space is so similar. Same thing with NavAir, working closely with the Air Force, and we have a lot of meetings to examine what are the areas of commonality, what are the challenges that we all have to face and solve together, how do we prevent parallel processes, how do we make it so that a vendor doesn't necessarily have to qualify to a tech pub ND20 and some exotic third standard. And the expectation is that a lot of that just comes through collaboration, communication. We have NAVC personnel on all the major boards. And the other avenue is that we respect that our application space is not the same as the air community or the ground community. The Marines do not need the same, the Marine requirements are different than what a carrier needs. The volume is different, the application space is different. And so we do the best we can to collaborate where there's unity, particularly in qualification and material standards. And then we allow the individual entities to really excel where they need to see success.
Got it. I think that's spot on. And so, with some of the challenges of so much documentation, right? Because even within the tech pubs, you reference many other supporting tech pubs or guidance documents. Are there any tools that are coming online to help kind of simplify digestion of those, or improve the process of folks being able to understand and kind of take action against some of those documents?
I will admit I am not aware of any tools. I imagine that they are out there. We have a ton of effort going into the digital realm, a lot of database management, a lot of understanding how it is that we can make the material specifications more readily available. I am not a digital expert by any stretch of the imagination. The gentleman who handles that, Louis Shattuck, is phenomenal and does very good things in pushing an extremely challenging problem in that avenue. Part of it is that part of it is that we need to understand exactly what the scope of the problem is. Is it useful to have a tool that shows what the qualification process is if it's AWST 20 and the Navy doesn't want it, or the NASA standard the Navy doesn't want it? what does DLA expect to have? So part of it is us understanding exactly where it is we need to go. And then part of it is that, you know, we're still figuring out exactly how to implement it. We're still getting vendors qualified. And the more we do that, the easier it'll be.
Yeah, I think that sounds about right. And we're getting close to time, so we've got like one or two more questions, and then I want to open it back up to you, Kevin, for some kind of closing remarks here. But um, going back to kind of the theory of AM and kind of determining the target materials of interest, right? Because we talked about Mill 100S serving as a replacement to the cast HY80. There's varying compositions of the nickel aluminum bronzes or the copper nickels, some of which make sense for casting versus maybe not making as much sense for different additive processes depending on the specific physics involved. So, what is sort of the decision making process for identifying, when does alloy really matter versus when do properties really matter in that transition from a casting to an AM part, even kind of independent or dependent on which AM process you're going to be using?
It's a tough question. And I get to once again weasel out and say it depends. Realistically, we care about interchangeability. I don't actually care what the material is. I care that the material does what I need it to. Conveniently, more often than not, what the material is will drive what alloying components are in there. And a lot of times what we'll do is we'll see alloying being tweaked gently so that it's more suitable for an AM process, but is still fundamentally doing what we need it to do. Now, there's another side of it, which is does focusing on interchangeability truly allow us to exploit all the unique capabilities of AM? And the answer is no. If I have a replacement for cast 316L, well, great. The material properties for 316L aren't that fantastic to begin with. Is that really going to leverage everything you can do with AM? Is it better to do that, or is it better to start designing for AM? And the answer there is that will be the next step. And at that point, it's not less about what are my material properties and how do they replace a valve that was designed in the 1950s, and more about what is my application space and what can I do to leverage AM to make things better. Everything from lightweighting is a perfect example. Navy components are huge. It turns out that when your primary requirement is to float and you've got a really big ship, you're not necessarily going to worry too much about whether or not a valve weighs 70 pounds or 80 pounds. But if you can start shaving off that weight here and there, if you can start saving 10 pounds here, 10 pounds there, all of a sudden now you're saving tons. And that translates to improved performance, improves, reduced consumption of fuel, all of those avenues. And the more that we see people embrace AM and design for AM, and the more we see people design for AM using materials that are uniquely suited for AM and have the material properties that are within tolerances that are reliable and producible, the better it's going to be for us in the long run.
That's awesome. I think that's a great way to think about the future. And we still have a pile of questions that we're never going to get to, so we'll send them over to you, and you can fire back to the team if you want them to. But with kind of the last minute here, give us Dr. Kevin Jensen's take on what are you most excited for in additive manufacturing over the next year?
So what I am most excited for additive manufacturing is for us to understand this trade space as much as possible, because what scares me the most about AM is us using it when we don't know what it is we need, what it is that it's going to be able to do. And the very realistic situation I am thinking about is what happens if we get hot? What happens if we start entering active conflict? Well, like any other environment, when you're in active conflict and the consequence of not having a capability is loss of mission capability, loss of life, loss of freedom, that encourages you to take risks that you're not necessarily going to take during peacetime. And our job in NAVC is to be the source of confidence in this process and in these materials. And the more that we understand it now, the more robust it is that we can provide those answers when the consequences are low. The better our job will, the better we can do our job when the consequences are high. So I take this extremely seriously, and I consider this to be as utmost a priority as we can have, because I know we will be asked questions that we have to have the answer for, and we cannot be wrong.
That is fabulously wise and very anticipatory. I love that response. So thank you, Kevin. And we really, again, appreciate you being willing to get out here, talk to us, answer some of the tough questions, give us the classic materials engineering it depends, which we all deeply appreciate, and really just be part of this community. Thank you for being on the board of LSAAT and helping us to kind of guide this ship and make sure that we're being a delivery platform for the community. So for everybody that's online, thanks for being with us. Again, large scale additive action team, check us out online or join us in June back in Worcester for another great series of talks around things like this, right? What are the challenges with large scale additive? Where's it going? What are the opportunities? How can we work together to move this technology base forward? And so with that, I think we can call it an afternoon, an evening, bid you all farewell. And again, thank you all so much. And Kevin, thanks again. We'll see you guys around.